Working rule for finding absolute extrema. Hello, everyone. Let's begin by recalling our previous lessons, where we explored the concepts of local maxima and local minima. To put it simply, these local extrema are like the peaks and valleys of a graph. They are points that are the highest or lowest only when compared to their immediate surroundings. However, in this section, we are moving beyond local points to look at the bigger picture. We are interested in finding the absolute maximum, which is the highest possible value the function reaches overall, and the absolute minimum, which is the lowest possible value it attains. For the purpose of this lesson, our focus will be on a specific, closed interval from A to B. Over the next few slides, I will guide you through the Extreme Value Theorem and a systematic working rule to help you identify these absolute extrema accurately. Extreme Value Theorem. Now that we understand the difference between local and absolute extrema, let's look at the theoretical foundation that allows us to find them, known as the Extreme Value Theorem. First, the theorem states that if a function f is continuous on a closed interval from A to B, it is guaranteed to attain both an absolute maximum and an absolute minimum value within that range. In simpler terms, as long as there are no breaks in the graph and we are looking at a fixed segment, the function must have a highest and a lowest point. But where exactly do these absolute values occur? The theorem tells us that these values can only happen in two types of places, either at the critical points located within the interval or at the boundaries, which we refer to as the endpoints of the interval. This is a very important realization because it narrows our search. Instead of checking every single point on the graph, we only need to check a few specific candidates. This leads us perfectly into our next slide, where I will show you the systematic, step-by-step working rule to identify these points and determine the absolute extrema. Step-by-step working rule. Now that we have established the Extreme Value Theorem, let us move on to the practical application. To find the absolute maximum and minimum values of a continuous function, f on a closed interval from A to B, we follow this systematic algorithm. Step 1 is to find the critical points. To do this, first calculate the first derivative of the function, which we denote as f prime of x. Once you have the derivative, identify all points, which we will call C, located within the open interval from A to B where either the derivative equals 0 or the derivative is undefined. These points are our primary candidates for the absolute extrema. Step 2 is to identify the endpoints. This is a simple but crucial step where we note the boundaries of our given interval, specifically where x equals and x equals b. As we discussed previously, the absolute highest or lowest values often occur at these boundaries. Step 3 is to evaluate the function. In this stage, we calculate the value of the original function, f of x, at every point we identified in the first two steps. This means we find the function values for all critical points, such as f of c1 and f of c2, as well as the values at the left endpoint, f of A, and the right endpoint, f of B. Finally, step 4 is to compare the values. We look at the list of results from step 3. The largest value among them is the absolute maximum value, and the smallest value is the absolute minimum value. By following these 4 steps, you can consistently find the global extrema of any continuous function on a closed interval. Now, let us apply this working rule to a mathematical example to see exactly how it works in practice. Mathematical example. Now that we have established the theoretical framework and the step-by-step algorithm, let us apply this working rule to a concrete mathematical example to see how it functions in practice. Please look at the problem on the slide. We are asked to find the absolute maximum and minimum values of the function f of x equals 2x cubed minus 15x squared plus 36x plus 1 over the closed interval from 1 to 5. We will solve this by following the 4-step process we just discussed. Starting with step 1, finding the critical points. First, we need to find the first derivative of the function. By applying the power rule, the derivative f prime of x is 6x squared minus 30x plus 36. To find the critical points, we set this derivative equal to 0. We can factor out a 6, giving us 6 times the quantity x squared minus 5x plus 6 equals 0. Further factoring the quadratic expression gives us x minus 2 times x minus 3 equals 0. Therefore, our critical points are x equals 2 and x equals 3. Since both of these values fall within our interval of 1 to 5, we must keep both. Moving to step 2, identifying the endpoints. As per our rule, we must also consider the boundaries of our interval. In this case, the endpoints are x equals 1 and x equals 5. Now we proceed to step 3, evaluating the function. This is a crucial step. Remember, we plug our candidate points back into the original function, not the derivative. First, at the left endpoint x equals 1, f of 1 equals 24. Next, at the first critical point x equals 2, f of 2 equals 29. Then, at the second critical point x equals 3, f of 3 equals 28. Finally, at the right endpoint x equals 5, f of 5 equals 56. Finally, step 4, comparing the values. We now have a set of 4 candidate values, 24, 29, 28, and 56. By simple comparison, we can see that the largest value is 56 and the smallest value is 24. In conclusion, the absolute maximum value of the function on this interval is 56, which occurs at x equals 5, and the absolute minimum value is 24, which occurs at x equals 1. Notice how the absolute maximum occurred at an endpoint rather than a critical point. This highlights why it is essential to check both. In the next slide, we will see how this same logic applies to a real-world business scenario. Real-world application example. Now that we have seen a purely mathematical example, let us apply the same working rule to a real-world scenario to see how these concepts function in practice. Consider a company whose profit is modeled by the function p of t equals negative t cubed plus 9t squared minus 15t plus 20, where t represents time in years, and we are analyzing the period from year 0 to year 5. To find the absolute extrema, we will follow the step-by-step algorithm we established in the previous slides. First, we find the critical points. We begin by calculating the first derivative, which gives us p prime of t equals negative 3t squared plus 18t minus 15. To find the critical points, we set this derivative to 0. By factoring out negative 3, we get negative 3 times the quantity t squared minus 6t plus 5 equals 0. This further factors into the quantity t minus 1 times the quantity t minus 5 equals 0. Thus, our critical points are t equals 1 and t equals 5. Second, we identify the endpoints of our closed interval. Since we are looking at the interval from 0 to 5, our endpoints are t equals 0 and t equals 5. Third, we evaluate the original profit function at each of these candidate points. At t equals 0, the profit p of 0 is 20. At t equals 1, the profit p of 1 is 13. And at t equals 5, the profit p of 5 is 45. Fourth, we compare these resulting values, 20, 13, and 45. We can clearly see that the largest value is 45 and the smallest value is 13. In conclusion, the absolute maximum profit is $45,000, which occurs at year 5, and the absolute minimum profit is $13,000, which occurs at year 1. Now that we have successfully applied the rule to a practical problem, let us move to the next slide to discuss some common mistakes you should avoid to ensure your calculations are always accurate. Common mistakes to avoid. Now that we have walked through the step-by-step rule and applied it to both a mathematical and a real-world example, it is important to discuss some common pitfalls. To ensure you don't lose marks on your exams, let's look at these common mistakes to avoid. First, one of the most frequent errors is ignoring the endpoints. As we saw in our previous examples, the absolute maximum or minimum does not always occur at a peak or a valley found via the derivative. It can often occur right at the boundaries of the interval. Therefore, always remember to evaluate the function at both the critical points and the boundaries. Second, be careful not to use the derivative for your final values. It is a common mistake to plug your critical points back into the derivative, f prime of x. Remember, the derivative is merely a tool to help us locate the candidates. To find the actual absolute maximum or minimum value, you must plug those candidates back into the original function, f of x. Finally, be mindful of your range. When you solve for critical points, you might find values that lie outside the specified closed interval. From a to b, you must discard any critical points that fall outside this range, as they are not relevant to the specific interval we are analyzing. By keeping these 3 warnings in mind, you can avoid the most common errors in this process. Now, let's move to the final slide to summarize our key takeaways. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of the process. First, remember that absolute extrema are the global highest and lowest points of a function over a specific closed interval. Unlike the local maxima and minima we discussed at the start, these are the absolute peaks and valleys for the entire range we are considering. Secondly, as we established in our working rule, the candidates for these absolute extrema are limited to 2 types of points: the critical points within the interval and the endpoints of the interval. Thirdly, the actual process is purely comparative. Just as we demonstrated in the mathematical example and the profit scenario, your task is to calculate the function values at all these candidate points and simply pick the largest value as your absolute maximum and the smallest as your absolute minimum. Finally, it is important to note that this method is universally applicable to any function, provided that the function is continuous and is defined on a closed interval. If you follow these steps and remember to check your endpoints, you will consistently find the correct absolute extrema.